Welcome back, everyone. My name is Pedram, and this is where we do machine learning codes and concepts. Let's get started.
All right, so let's do the Python part for module number 10, which is bagging and boosting. So I'm going to do it in two separate videos because there's a lot to cover when it comes to the Python. And in the first one, I will talk about bagging in general, do a regression and classification task. And in the next video, I will do a boosting. And we're going to cover all the boosting techniques that we talked about in the theory lecture. AdaBoost, GBM, XGBoost, CatBoost, and LightGBM. So let's start with the bagging part. So going to the course, Machine Learning USU, and then go to Lectures and Code. Module 10, bagging and boosting. Go to the Python folder. There are two subfolders, bagging and boosting. So here's the bagging. And as you can see, there are two notebooks. One is random forest classification. The other one is random forest regression. So I'm going to have both of them open. And if you click on this open in Colab, it should work. And it should take you to the right notebook for both of them. And yeah, so this is regression, this is classification. And again, because I have PyCaret already installed on my local computer, I don't need to install it again, so I'm going to run things locally. But if you're doing it on Google Colab, you have to go ahead and install PyCaret from scratch every single time. Okay, so and then the dataset that we're working with is one is classical house pricing regression task, and the other one is credit card default detection, right? So we want to see if someone is going to default on their credit card or not, right? So yeah, we have seen both of these data sets before. So in terms of EDA, we don't need to spend some time, but maybe we need to talk about some details. Okay, so let's open up these are the files that I have, right? Random forest regression, and then random forest classification, and then in the next video we're going to do all the boosting classification techniques. Okay, so let me select the right kernel. So I have PyCaret already installed on my computer, and then so this is PyCaret, the full version, by the way. So if you want to get access to the CatBoost and LightGBM, you should install the PyCaret full version. I'm going to show it to you how to do that, if you don't remember it. But for now, we are going to do the Scikit-Learn package first, and then at the end of it, we're going to do the PyCaret. Okay, so let's import the relevant libraries, and here's our data set. So I'm gonna, well, actually, while it's loading, because I'm just running it, it may take some time. I'm gonna look at the head of the data set. So this is our data set, right? Basically, what we're going to predict is sold price. And based on some interesting features, we have DOM, which stands for days on the market. We have garage capacity, HOA fee, irregular shape, quadrant, school district, sold term, total bedroom, bathroom, square feet, year built, zip, year sold. And based on this date sold, we created two other variables. One was year sold and one was month sold, right? And then we also created a dummy variable for year built, because this is our year build, and we're going to see that we have too many different levels for year build, and we thought that if you want to treat it as a categorical variable with other machine learning models, maybe we should add it as a dummy variable, build after 2000 and before 2000, right? But here we are dealing with random forest, and we know that random forest and bagging in general, or decision tree based models in general, can handle categorical variables without increasing the dimensionality of the data. So this is a nice feature. We talked about this cool feature of random forest in the theory lecture. So check it out if you need a refresher. All right, so this is a task, right? So let's quickly look into the data info. So there's no missing variable here. This is all good. And then the type of some of them are objects, right? So we need to fix them because this means that these are strings, right? Irregular shape, quadrant, school district, and solver. These are strings. Even though they're categorical and random forest can handle categorical variables, but it cannot handle a string. So we have to go ahead and change them to some numbers, right? And in order to do that, we're gonna use label encoder. For example, I don't know, for quadrants we have 4 values. We have to call them 0, 1, 2, 3. And the same is true for school district, sold term, and etc. etc. Okay, so you should keep in mind that by default the random forest cannot handle strings, so we have to fix it. So again, the dataset is pretty much clean, no missing variables. We just quickly check if there's duplicates, and it seems that there is, so we're going to drop that duplicate. And now here's a function that we have been using consistently in the past to make sure that what should be the type of variable. Should they be continuous, or should they be numeric or categorical, right? So sold price obviously is numeric, days on the market numeric, the garage capacity, it can be numeric. HOA fee, numeric, irregular shape, this should be categorical, right? We have only two categories, and obviously it should be categorical. Quadrant should be categorical, school district categorical, sold term categorical, total bedroom, bathroom, and square feet, these should be numeric. Year built, even though there are 136 different values for year built, but I would rather to treat it as categorical. The reason is that if you believe that there's a nonlinear relationship in your random variable, then you should treat them as different categories. You can make it a categorical variable. That's the case here, right? Or I don't know. For example, if you calculate a ratio and if it makes sense, then it can be continuous or numeric. If it doesn't make sense, then you can treat it as categorical, right? The same story for zip code. Obviously, year sold should be categorical, and then month sold should be categorical as well. And then built after 2000, obviously it's categorical, right? So this is built on top of year built. So we can go ahead and remove this, but I'm going to keep it in the model and see, because with random forest we have feature importance, and then we can see if it is any important at the end of the day or not, right? So now let's talk about the encoding part, right? Because honestly, doing these things using Scikit-Learn package is super easy, but preparing the data is a more challenging aspect of it, right? So let's talk about this regression task, and let's prepare the data. Let's encode the data first, right? So as I said, the random forest or decision tree based models can handle categorical variables. However, they cannot handle strings, right? So we have to make sure that these strings are numeric. So let's start with them, right? So I'm going to go ahead, and so I already talked about this zip and year sold and etc. So feel free to pause the video and read this for your own. So these are going to be my categorical variables. These are general categorical, right? So year built, year sold, month sold, and built after 2000. And so I'm going to run this line to make sure that all those categoricals are literally categories, right? So now year built, year sold, month, and this one are category variables, right? And for random forest, honestly, as long as these variables are integers or numbers, it really doesn't make a big difference, right? Because either we see year built, let me show you something. This is important, so pay attention to that. Look at year built. It's 1974, 1995, 1980s, and etc., right? So even if I don't change it, it's numeric. Even if I don't make any changes and pass it to the random forest, it can handle it. Basically, when it wants to make decisions, split the data, it's going to look at these cutoffs, and it's going to consider anything. So it really doesn't matter how many levels we have. At the end of the day, we're going to have one random variable, and then the random forest is able to handle that one variable, right? But in order to make sure that it is, we are doing the pre-processing correctly, and this should be a categorical variable, I'm going to go ahead and specifically make it category, right? So now we know that these are categories. So again, just for short, if I make these numerical values to category or not, it really doesn't matter. Random forest can handle it. But what about auto models? They cannot. So that's why I want to do the pre-processing part properly. So that's one thing. But the cool thing is that I don't need to go ahead and use one-hot encoding for year sold or month sold, right? If it is any other machine learning model, I have to do one-hot encoding to handle categories. But random forest, we don't need to, right? So we talked about the details in the theory lecture. So that's it. These are the categorical variables. And we know that there are some other variables that were string, like this, irregular shape, quadrant, school district, and sold term. Yeah, I think the zip shouldn't be categorical, so I can remove zip because we already took care of zip here. Oh, let me see. No, zip is also a string. Yeah, it's 84335. Yeah, it's integer, but again, anyways, it really doesn't matter. We can either leave it like this, or we can label encoded, right? So let me tell you what I mean by that. So from the Scikit-Learn pre-processing, we're going to import label encoder, and these are the variables that I want to replace them with numbers from 0 to whatever, how many number class we have, right? So that's, let's look at the head of this variable. So basically this is from our data frame. We're going to make a list, and this is our labeled categoricals. We're going to change them, right? We're going to change the type of these things into label encoding, right? So let's see, what does this label encoding do? And again, as a reminder, why are we doing that? Because we believe that these should be categorical, okay? So I'm going to create an encoder. I call it LE, stands for label encoder. And I can do fit transform. I'm going to show it for one of the variables, and then we're going to put it in a for loop or list comprehension to do all of them together. But I just wanted to show you what it is doing under the hood, right? I have a label encoder now. I'm going to apply to the quadrants variable. Let's go back. Remember, this is our quadrants variable. Northwest, northeast, southwest, southeast, right? So we have 4 of them. So if I apply that label encoder, LE label encoder, if I do fit transform to the entire data set and to all the observations for the quadrants variable, this is what we get, right? So, and then I can look at the classes from this label encoder. Basically, you can get access to a bunch of stuff, right? So you can look at the classes, you can look at the parameters that was used for the fit and transform, and et cetera, right? So these are the classes, right? And this is the ordering. So northeast, northwest, southeast, southwest, and it should be labeled as 0, 1, 2, 3. Okay, so when you see a number 1 here, it means that it is northwest. So the first 3 observations are northwest, northwest, northwest. Let's check it out. Northwest, northwest, northwest. So there you go. So it's doing its job, right? And now that we know what is happening, let's put it in a nice for loop and then do all these label encodings for these features, for these features, right? Irregular shape, quadrants, school district, sole term, and zip. So let's do that. So this is, and in order to make sure that we are keeping track of the mappings, I'm going to make a new dictionary, call it mappings, and I want to save the, basically save the classes, right? Because who knows, for interpretability, maybe later on you want to get access to those mappings, right? So for example, you want to see for zip, what does number 4 stands for? For sole term, what does number 3 stands for? And if you want to do that, so you have to make sure that you're saving those mappings, right? Okay, so I'm gonna go ahead and run it. Oopsie. So it's not defined. Let me see. It says that labeled categorical is not defined. We did define it. Let me see. Yeah, labeled categoricals. Maybe there's a typo somewhere. Let me just check it out if there's no, it should work. Okay. Yeah, then here's the mappings. Again, now we know that what are the mappings? Well, let me actually, yeah, that should work. So irregular shape is array no, yes. So basically these are, this is the first one, 0. This is the second one, okay. And quadrant, school district, sole term, and zip. So here is our mapping. Again, for the modeling part, we don't need them. But later on, who knows, if you want to do interpretability things, if you want to keep track of those mappings, so this is a way to do that. Make a dictionary and save those things. And we're not doing anything fancy. We're saying that for all these columns in label categoricals, go ahead and create this encoder, train it, and then apply to that specific column. And now in this is a dictionary, remember, key and item. You know, so for call it column, it's going to be the name of the column and then the classes. So these are going to be the classes. Okay. Sweet. And then we can go ahead and change the type of these things. Remember, now let me actually show you what we have right now. So if I look at the df.head, so this is what we have. So for quadrant, it's not string anymore. So these are numbers, right? School district, sole term, same story. If I pass something like this, and for zip codes, to the random forest, it can absolutely handle it. So don't get me wrong. So because these are integers, even though some of them we know that they're categorical, we don't need to make any changes. However, in order to do this pre-processing, correctly, let's specifically set them to categories, because later on, if you want to use another machine learning models, this data set has been pre-processed correctly, okay? So I can go ahead and say that, you know what, all these labeled categoricals, these 4 ones that we did, 1, 2, 3, 4, 5 of them, let's change the type to category, and then look at the data frame information one more time. Now the data is ready, right? So we have all our categorical variables as category, and their value is basically some numbers, right? Because we use the label encoder, they are not a string. So we can pass this to the random forest model and then see how it works, okay? So just here's a quick comparison between if you want to do things in random forest versus other machine learning models. In the theory lecture, we said that one of the biggest advantages of decision tree based models is that it can keep the dimensionality of the data set low, because we don't need to one-hot encode all the categorical variables. In parentheses, you can if you want, and actually you can try both and see which one performs better, but you don't have to, okay? So, well, typically you can try both and see which one is better. Now, if I wanted to, let me show you the unique values one more time. If I say df dot number of uniques, number of unique values. So as you can see, we know that these are categorical variables. So for example, irregular shape 2 plus, if I want to do one-hot encoding, so I have 2 variables here, 4 variables here. Well, you can drop the first, but you get the idea. I have 2 here, 6, and then I have 136 here, 16 here, 3, 12, and 2. If you add these things, you get more than 180 features. So if you want to work with any other machine learning model, you have to, the dimensionality of the data is going to be 180 plus. But with random forest or decision tree based models, we can keep it as low as 15, because I believe one of them is going to be, sold term is going to be, sold price is going to be the target variable. So we have 15 features. So this is very, very interesting, right? So we don't need to go to 180 plus dimensions. So we can stick to 15 or 14 dimension, and it should be 15 here because we ended up not dropping the built after 2000. Okay, if you drop the built after 2000, you can say we have 14 features. Okay, it's not going to make a big difference. All right, sweet. Then for feature scaling, we don't need to scale the features, because I think in decision trees we also talked about it. These are tree-based models. We don't need to scale the features. Okay, cool. So now let's look into basically splitting the data. So we can set the random state to 1000. You can do that if you want to get the same numbers as I do. So our target variable is going to be sold price. Our features are going to be everything but the sold price. We're going to do 30-70 split, 30 test set, 70 train set. Okay, and that's it. We are ready to run our random forest regressor model. So just like any other machine learning model, let's go ahead and import that one from Scikit-Learn ensemble modules, right? So this is, as you know, this is one type of ensemble learning, right? So we are putting together a bunch of weak learners, i.e. decision trees, to make a strong learner, which is in this case random forest. And if you're wondering, do we have a separate class for bagging? The answer is no, because I will talk about it. This random forest, if you change one of the features, it's going to become bagging automatically, right? So basically, if you set the max feature to use all the features, that's it. It's going to become bagging. And in the theory lecture, we talked about it, but I'm going to pull up the documentation now and then show it quickly. And so this is plain vanilla random forest, right? So we have our object regression. This is our random forest regression. Once we have it, we can go ahead and fit to train data set. So there you go. The model has been trained. Let me see. Well, I haven't run this one. Okay. So there you go. Now the model has been trained. Okay. When the model has been trained, we can make some predictions, right? So this is regression. So if I use the predict function, it's going to go ahead and to make some prediction in the test set. There you go. So these are our y-hats, right? And before I move further, I want to show you the documentation of random forest regressor, and it's going to be pretty much the same for classifier as well. So this is documentation for regressor, this is documentation for classifier. So I'm going to walk you through this one, and then for classifier it's going to be pretty much the same, just with a few changes. So what are the parameters we have? Number of estimators. So this is how many trees you want to have in your forest, right? So by default it's 100. So the higher this number, obviously we can make the model more complex. Probably it's going to do better in train set or sometimes even in the test set, but it comes with computation cost, right? So we can tune these hyperparameters, by the way. We can say, hey, go ahead and try 100, 200, 500 and see which one is better. Criteria, this is regression, so we're going to stick to our mean squared error. So this is pretty much standard, so we are not going to change it. Max depth, so this is the max depth of the tree. So we have talked about all these hyperparameters for decision tree models in general. So I'm not going to talk about the details, but I will specifically talk about those things that are related to random forest. Okay, so mean sample split, mean sample leave. So these are our regularization parameters if you wish. This is specific for random forest, right? So max features. By default, it's basically 1, and 1 means max feature is equal to all the features. So this means that if at every single split you're using all the features to go further down in the tree, then this is our bagging process, right? If you use a subset of those features to decorrelate these tree even further, then that's called random forest. So by default, if you don't do anything, your model is doing bagging. So if I go back to my notebook, to my Python notebook, so this is basically, because we're not setting anything here, so this is basically bagging, not random forest, right? If I change the max feature to, I don't know, to use a square root or use log or something like that, then, so this is something I show you in the theory lecture as well, then that's going to be random forest, right? So basically using a subset of features at each split is going to make sure that the new trees are more decorrelated, or even more decorrelated from each other. Okay, so the variance is going to be smaller, the model variance. I think this is the most important part of random forest model. Then what else do we have? Max leaf node, mean impurity decrease. So we have talked about all these things before. And there's another thing which is just for random forest or bagging models in general. That's the bootstrap thing, right? Because remember, for each, so let's say we have 100 of these decision trees in our forest, and we don't want to use the same data set. We're going to use bootstrap. So bootstrap is sampling with replacement. So out of and let's say you have 1,000 observation. Out of 1,000 observation, 2/3 of it is going to show up in each bootstrap, in each sample. So by default, bootstrap is equal to true. So just pay attention to that, because otherwise we're not doing random forest, right? If I set the bootstrap equal to true, I can go ahead and calculate out of bag scores as well. So I'm gonna postpone this thing until we get to the Python part, and it's easier to explain it in Python. But in a nutshell, what we're doing, we say that go ahead and calculate the out of bag, if it is regression, out of bag R square when you are training the model. So what does it mean? It means that if you have 1,000 observations, 2/3 of it is going to show up in the bag for each tree that we're putting together. So 1/3 of the observation is on average. It's not going to show up in the in your training process. So this means that 1/3 of the data has not the model has not seen this 1/3 of the data. So we can call them out of bag, right? And if we make some performance metrics, if we calculate performance metric for the out of bag observations, so that's going to be awesome, right? So this is basically an estimate for the performance of the model in the test set. So we can switch it on or off, right? By default, it's false. It's switched off. If you turn it on, it's going to take longer for your the random forest to be trained. Number of jobs, if you set it to -1, it's make sure that it's using all the cores in your CPU, and then random state, verbose, yeah, CCP alpha, cost complexity pruning method, and yeah, that's pretty much it. These are all the ingredients of the random forest that you can play around with. Now let's go back to the notebook. Okay, so now we know that this is a bagging model, right? Because the max feature is equal to number of features. These are our predictions, so we can put it in a nice data frame. These are actuals versus predictions. When I have actual versus prediction, this is regression, right? I can go ahead and look at the y hat plot, and if it is a good model, everything should line up across the 45-degree line. It's doing a decent job, actually. I can go ahead and report the RMSE as well. And by the way, this is, if I do random forest score, by default score for regression is R squared. So I can look at this R squared in test set, which is 83%. Okay, it's doing a decent job. I can check the R square in the train set as well. So if I do X train and then Y train, obviously it's going to be better, but hopefully our model is not overfitting. So it's 97%. So it's in the train set, it's 97, it's doing 97. In the test set, it is doing 83%. So it's doing okay. I can go ahead and report the RMSE as well. So this is the RMSE, 46,624. What is the unit? The unit is the same as your target variable, which is dollars. Okay, so this is sold price. So this is $46,624. And then you have to go ahead and compare this performance metric with other machine learning regression models and see which one is lower, right, in general. So we talked about these two hyperparameters as well. So these are the most important one in random forest. The bootstrap can be on and off, number of estimator, this is number of trees in the forest, out of bag scorer, max features, and then that's it. So again, feel free to just pause the video or just read the notebook. This is what I explained on the documentation part. Okay, now let's say we want to find a good combination of all these features, right? So far, the models that we covered, they either had one or two hyperparameters, and we didn't talk about tuning hyperparameters in decision trees. There is a reason that no matter how hard you try to make a decision tree perform better, random forest is going to do better. So let's not waste time and then tune a decision tree if you don't want to visualize a decision tree, if you don't want to use the model for interpretation. If you want to use a model for interpretation, it is worth spending some time, tuning decision trees as well. But here we're talking about the random forest, and we care most about the performance of the model, right? So what is this idea of grid search? So the grid search is that we are going to make a grid of parameters, right? And then we are going to look into every single combination of those parameters, right? So what do I mean by that? So I'm going to go ahead and create a dictionary. I call it my parameter grid. And you can play around with these numbers. So for example, number of estimators, how many trees you want to have in your forest. Go ahead and try 10, 100, 500. What do you want for max features? You can go ahead and say sqrt log2, or you can also add none here. If you add none, it means that you are comparing random forest and bagging at the same time, right? Max depth 5, 10, 20. Where do I pick these numbers? No idea. You have to try it and see which one works better, right? So for example, you say 5 and 10, and the model is picking the best parameter is 10. So you know that 10 was a small. So you go to 20. If you go to 20, the model is again picking 10, so this is going to be your optimal number. But what does it mean? Does it mean that grid search is going to always give you the best combination? As you guessed, no. Why? Because again, the universe that you can basically explore in terms of different combination of all these parameters is it's limitless, right? So here, just for the sake of the teaching purposes, I'm going to show you how to do grid search. And it's not completely random though, right? We have random grid search as well, which is speed up the process, but that's beyond the scope of what we are covering here. So let's say these are my parameters that we want to explore, right? So I have 3 number of estimators, I have 2 values for max features, and I have 3 values for max depth. So in general, how many combinations can we have? 3 multiplied 2, 6 multiplied 3, 18, right? So we can have 18 different combinations. So just remember that number. Then I'm going to go ahead and say from model selection, go ahead and import grid search, because remember guys, we are doing cross-validation to find the best combination of hyperparameters. This is basically what we're doing, right? So it's called grid search cross-validation, and now we're going to create an object called grid. This grid is nothing fancy. It's just grid search cross-validation. So under the hood, we are borrowing this function from Scikit-Learn. What it is doing, it's saying that go ahead and use random forest regressor with these parameters, all these combination of these parameters, and then give me the best one. If you want to make sure that it gives you the best one, you have to say refit is equal to true. It means that when you found the best parameters, go ahead and refit the data set one more time with the entire X train and X test, and then save those numbers. So this is what this refit is equal to true is doing. Verbose is equal to 2, it tells you that how many level of information do you need, right? If I set it to 0, it's not going to show anything here when it's going over the grid search, but you want to see something. So that's why I set it to 2, and then 5 cross-validation, right? Remember, we have 18 different combinations. For each of them, we have 5-fold. So 18 multiplied 5, we get 90, right? 90. So this is, if I run this line, so this should be, this should be fast, but I don't want to slow us down. So so you can go ahead and run this line, but basically it's going to do something like that. Well, actually, let me do this for classification. I'm going to skip it. So let's do grid. Oops, my parameter grid. I haven't run this one. So there you go. So this 90 is coming from there, right? So max depth 5, SQRT, number of estimator 10. And we have 5-fold for this. Then the next one is max depth 5, SQRT, number of estimator 100. We have 5 of them. Then we have 5 for 500, and etc., etc. And as you can see, we are running this 90 different combinations, well, 18 different combinations with 5-fold each, so 90 times you're running through the model, and then we're saving the best one, right? Once it's done, you can say this grid, this is the object that you train, go ahead and off of that, give me the best parameters. So the best parameters in this specific grid search is 20, SQRT, 500. And as you can see, it's hitting the borders, right? So it means that maybe 20 was not large enough. So maybe I need to go even beyond. Maybe I should do 30 and see if 30 is better one. Or even 500 was not large enough, so we can do 1000, right? But you get the idea. So you have to play around with these numbers. So this is the art part, right? And so this is our best estimator. Again, with these parameters, let's remember them because we're going to use them later on, right? Max depth 20, SQRT max features, and then 500 estimators. Okay, so we can make some predictions. I call it y-hat optimized, and we can compare the performance of this optimized version versus plain vanilla bagging version, right? And we know that this is going to be random for us because max feature is equal to SQRT. It's not using all the features. It's using a square root of the features. If you have 100 features, it's using 10 of them at each split. Okay, so these are the optimal values, and we can now look at the basically, remember our prediction, this was actuals, this was bagging, now this is random forest because the max features is square root of number of features. Okay, sweet. We can go ahead and plot y versus y hat for the optimized value as well, but it's hard to tell anything. Like here, it's doing okay. So here we are kind of off, but overall it's not bad. But we can look at the performance in the test set. It's 85. So it used to be 83% in bagging. Now it's 85% R-squared, which is better. And also the RMSE decreased to 44,634. It used to be 46,624. So there is a slight improvement. So in general, random forest is better than bagging. Okay, in this case. All right, now we want to do basically, look at this number, RMSE. This is performance of the model in the test set, right? 44,634, right? How can we estimate this number? Remember, we can, if it is any other machine learning model, we can use cross-validation, right? But here, this is random forest, so we can do cross-validation and we can use out-of-bag observations, right? Because remember, these out-of-bag observations are the observations that the model is not seeing when it's being trained, right? So let me try to demystify why that's the case. So first of all, let's use cross-validation to estimate this number, and then we're going to do out-of-bag. So we have done this multiple times before. So from model selection, let's import cross-validation as scorer. So then we're going to do R-square. So I could have done negative mean squared error and then basically take the square root of that and then call it root mean squared error. But here, just for simplicity, let's look into this. Let's try to estimate this 85%. So the model is going to be random forest. The optimized version, remember, was max depth 20, SQRT 500, number of estimator, and then 5-fold. If you do that, you're going to get 77.97%. So this is an estimated value for, well, so again, there's this random component, 7784. Estimated value for this 85%-ish. Okay, so this is pretty close. Well, not pretty, but again, this is the best guess we can have for the performance of the model in the test set, if you don't want to use the test set, right? So how else can we estimate this number? How else can I estimate this 85%? And the answer is out of bag, right? So now let me show you what I mean by that. Imagine this is from NumPy. I'm using random module, and this choice basically tells me that go ahead and create 100 numbers between 0 and 99, not including 100, right? So I can change it to 101, then the 100 is going to be there as well, right? So go ahead and create. So every single time when I do Control Enter, every single time when I run this, it's going to create 100 different random numbers, right? Okay, between 0 and 100 in this case. Now I can say, can you count the number of unique? So let's do 101 to be consistent. So I'm going to say how many of these things are unique, right? Because this is basically sampling. When I use the choice function, it's sampling with replacement. So you're going to see some of them being repeated, right? So it's hard for me, I guess, to visually find some of those repeated ones, but we can definitely use this NumPy unique function to tell us how many of them were unique, right? So this NumPy unique function is going to give us the unique ones. Well, actually, let me remove the size. So these are unique, and then if I do size, it's going to tell us how many of those variables, how many of those numbers are unique. 64. So as you can see, about 2/3 or 66% of the data, when you're doing sampling with replacement, is going to be repeated. So we're going to call them in the bag. And 1/3 of it is not going to be repeated, right? So if I run this multiple times, we get a different number. But if you take the average, on average, it's going to be 66%. Hope you get the idea, right? So this means that every single time that we are creating a decision tree, remember, this is a forest of trees, right? We have 500 of these trees, or let me see how many. Yeah, we have 500 of these decision trees, right? Let's say we have 500 of these decision trees, and every single time we are using these information, right? And 33% of it is basically not showing here, right? If I have 100 observations, 2/3 of it is in sample, 1/3 of it is in out of sample. So we call it out of bag, right? So that means that for each decision tree, we can go ahead and use those out of bag observations to make predictions on those observations and then calculate the performance metric, right? So for example, in tree number 1, I train a model on 2/3 of the data, original data. And because why do I say 2/3? Because the rest is going to be repeats, right? And then train a model, make prediction on the 1/3, which is out of bag, and then save that number. So I'm going to have 500 of those numbers, right? So I'm going to have 500 of those out of bag R-squares or RMSEs. And I take the average and I report it back. This is what out of bag is doing for us, right? Automatically. And it's a very fair estimate of the performance of the model in a test set because the model has not seen these out of bag observations, which is great. Each decision tree has not seen its out of bag observations. So if I want to create that object, I call it random forest out of bag. This is our typical random forest regressor, max depth 20, SQRT, number of estimators 500, and now I'm setting out of bag score is equal to true. So go ahead and do that. Calculate, again, because we have 500 trees here, calculate those out of bag R squares 500 times, take the average, and then report back the average. What is that average? So this is the object that you trained. Off of that, there is this method you can call out of bag underscore score underscore, right? So this is your R squared. So R squared is reported. Sweet. So this is 77.6%. So this is pretty close to our cross-validation R squared, right? And both of them are fair estimate of the performance of the model in the test set, which is this. Great. So I'm not going to repeat this part. I'll leave it as an exercise when we go over the classification, the notebook. So just be aware. When I say that here, when we get to the classification notebook, I say that can you do it on your own? So you have to refer back to this, or you have to do it from scratch, or you have to use ChatGPT and then or Google Bard to do it on your own. Okay. All right. Another cool thing that I really like about random forest or decision tree based models in general is the feature importance, because it can sort the importance of the features for you. So we talked about the details of it in the theory lecture, but here in the Python, we're just showing it to you how we can do it and how we should interpret it, right? So I'm going to go ahead and create a list of features. So these are our feature list, starting from days on the market and all the way to the built after 2000. And then I'm going to go ahead and train another model just for last time. I call it random forest regressor. We don't need to keep track of the out of bag observation. So that is set by default is going to be equal to false. So this is our trained model, right? All right. Now, when you have this trained model, you can say, in general, when you're working with Scikit-Learn package or any other packages, when you have a trained object, if you go ahead and say dot, it shows you what are available features, what are available attributes that you can use, right? So here, for example, I'm going to use, let's see, we have some feature. I'm going to use feature name, or yeah, we can do feature importance, feature names we can do as well. So let's look at feature names. So these are going to be the feature names, right? And then the next one is feature importance. So this means that DOM, this is the number for feature importance. Garage capacity, this is a number for feature importance. Obviously, it's hard to read it this way. Let's go ahead, put it in a nice data frame and sort it, right? So I'm going to say create a data frame. The features are feature names. The feature importance are feature importance of this object. Go ahead and sort them by feature importance and then save it as a data frame and show me that data frame. So this is a lot easier to read. Now I can say it seems that irregular shape is the least important one, and total square feet is the most important one when it comes to predicting house price. That makes sense, right? So it really doesn't matter. Well, it's not really doesn't matter, but in this case, it's the least important one, right? Surprisingly, school district was the least important one as well. Well, among the least important one. But the top performers are what? Total square feet, perfect sense. Garage capacity, interesting. I was surprised. Total bedroom, bathroom, perfect sense. Make perfect sense. Yeah, you get it. And then I can visualize it in a nice bar plot, right? So this is a lot easier to read it this way. So this is what we showed in the theory lecture and it talks about. Again, don't worry about the magnitude. What matters is that which one is most important. So total square feet is most important and irregular shape is least important. You can compare the magnitude. So for example, it seems that it is twice as important as this one, but don't try to read too much in terms of the numbers, but because these numbers can change and you can normalize it anyways, right? You can go ahead and divide it. You can take the sum and then divide everything by the sum and then normalize it in terms of percentage. All right, that was the Scikit-Learn part. So now let's talk about the PyCaret part. Okay, just like any other machine learning models that we have covered so far in this course, so PyCaret is able to handle random forest as well. So here's the documentation, the model containers. Again, it's a very good idea to read the PyCaret documentation in very detailed. This is a very well documented package. And look at the model container. If you wanted to tune the hyperparameters, you have to see what is the grid search? Basically, what are the values that we are searching over when you're doing tuning hyperparameters, right? So for example, here, this is regression. I can search for random forest. I think I need to do random forest. Yeah, random forest regressor. Classifier is also here. But if I scroll down, these are my tuning hyperparameters, right? So, and the numbers. The tune grid is, for estimators, we go from 100 to 300. So for example, if you want to ever try 400, 500, so you have to use Scikit-Learn and do it from scratch. So just be aware. This is really important. Max depth goes from 1 to 10. This is minimum impurity decrease. What else? Max features. We have, again, bagging, SQRT, log 2. So this is bagging versus random forest, and you will see which one works better. Bootstrap. This is interesting. True, false. And yeah, some other distributions, number of estimators, max depth, and that. So these are some basically the distribution for those features. All right, so let's go back to the notebook and wrap this regression part up. So installation, again, if you're doing it in Google Colab, run this thing, pip install PyCaret. Actually, you have to install, well, for this one, you don't need to install the full version, but for the boosting part, because we want to get access to the cat boost and light GBM, you have to install the full part. For this one, I'm going to leave it as like this, so you don't need to install the full version. And all right, so by the time you're watching this video, the version of PyCaret is 3.1. Not by the time you're watching, by the time I'm recording this, right? Which is basically we are November 2023. And so I'm not gonna run the PyCaret cells. I'm just gonna walk you through it because we have done this many times before. But let me quickly walk you through that one. So this is a raw data without any pre-processing. But the cool thing is that with PyCaret you can say pre-process is equal to true, and it's gonna take care of everything for you. So from regression, import everything, and this is how we set up our experiment. So I can call it exp. This is experiments, and if I don't do it, it's gonna automatically just assume that there's only one experiment and then go. But here I just wanted to show you something that we didn't cover in the previous videos. So I'm gonna go ahead and say this is my data, this is my target variable, and then let's do the same split, 30/70, pre-process equal to true. If I run this, then you see that it seems that automatically it's capturing 2 ordinal features and 11 numeric features and then 4 categorical features, right? It's a good idea to check it out what PyCaret is doing. So if I say exp._fx, so I think this stands for features or something like that, fx's, and then it's going to tell you what's going on, right? So we're not ignoring anything. It's a dictionary, right? The ordinals are going to be irregular shape or school district, and numerics are these ones, and then categoricals are these ones, right? So, and you have to double check that if the ordinal makes sense or not, right? Here, because we have only 2 classes, it really doesn't matter if I assume that irregular shape is ordinal or not, right? Or school district. So this is, for example, Logan district versus Cache district. We don't want to say which one is better than. Basically, there's no order here. But because this is only 2 class, it really doesn't matter, so we can move on. So I'm happy with this pre-processing that PyCaret is doing, so I'm going to move on. So let's set up using, again, that pre-processed data, and now off of that, we can look at the models. So these are the models. We have covered quite a few of them so far. Now let's talk about random forest. So where is the random forest? It should be RF, right? So random forest regressor. And as you can see, it's directly coming from Scikit-Learn. So you know how to work with Scikit-Learn, and this is basically using that one. All right, so we can go ahead and create a model. So we have done this many times before. So create model, estimator is going to be random forest. And this is our regression model. R-score 85% for 10-fold cross-validation. So you can, for example, change fold to 5 if you want to do 5-fold cross-validation, or you can play around with some of the features of random forest as well. We can tune this thing, and this tuning is going to take some time, so that's why I did 5-fold. But here's the interesting part: even though we call it tuning model, and the performance went down from 85% to 83%. So this 1 or 2% might not be significant, especially because the standard deviation is 2.2% here or 1.6% here. But in general, here we are seeing that on average, the tuned version is not better. So why that's the case? The reason is that probably those parameters that you're looking for, it was not enough. We couldn't find a best of combination here. So specifically, look at the number of, where is that? The number of estimator. So it goes all the way to 300. It doesn't go anything beyond that. So maybe the answer was 500, right? Okay, so yeah, that's it. We can do some plot models for regression. Here are the parameters of the tune model or the basic model. So these are parameters of the model you can get access to. We can look at the residual plot, R-score in the test train set, and the normality of residuals if you care. And we can finally look at the learning curve. So in the train set, this is a bushy tree and bushy forest, it seems. And it's doing awesome in the train set. There's not much room to improve in the train set, but we know that if these things are converging, the cross-validation score and train are converging, it's a sign that the data is kind of begging for more information, for more observation. That's the case here. So if I could go out and collect more information, so probably we can do even better when it comes to performance of the model in the test set. So here, cross-validation, it's sitting at around 85%, which is not bad, right? This is a regression task. And feature importance is another plot we can do. Total square feet was the most important one. This is consistent with what we got when we did things manually. But I personally, and this is it, I personally prefer to do things using Scikit-Learn. So I use PyCaret as a tool to quickly, especially if the data set is a small, right? A couple of thousand or I don't know, 10,000, something like that. If the data set is a small and if your task is a straightforward, I would like to do PyCaret to run a horse race between all these models and then see which one is the best one, pick the winner, and then work with the winner or a couple of them, or put together a bunch of those winners and then build them from scratch in Scikit-Learn. Because Scikit-Learn is more flexible, I can have fun with it, right? Okay, so that was the regression part. And next, let's do the classification part. But because this is already have been a 50 minutes kind of video, I don't want to make it even longer. So I'm going to do the classification, the random forest classification in a separate video. So in this one, we covered random forest and bagging regression models, and we did it both using Scikit-Learn and PyCaret. Until the next one, take care.